Hello everyone, I am Tanmay Namdar. The title of our paper is Capacitated Sum of Radii Clustering, an FPT approximation. And this is a joint work with Kasturi Varadarajan. So let's talk about clustering. So one way to make sense of the data that you have is to find natural groups or clusters in the data. And the way you typically do this is by encoding the data as some points in some space by using some features of the data. And this encoding comes with an associated distance function, which is a measure of similarity, which means that if the two entities in the data are more similar to each other, then the associated points will be closer together. Right? Now let's look at clustering more formally. So suppose we are given a set of points P, and let's say D is the distance function, and we'll assume that D satisfies triangle inequality. So it's a metric. And we want to find a set of at most K centers, and then assign every point to a nearby center so that we get a bunch of clusters. And there are many clustering objectives to analyze the quality of the clustering that we found. And let's look at a couple of these clustering objectives. So in K center, the cost of a cluster is the radius of that cluster, which means the maximum point center distance in that cluster. And the overall cost of clustering is just maximum such cluster cost. Next, we have K median. So here the cost of a cluster is the sum of all point center distances in that cluster. And then the overall cost is just the sum of all the cluster costs, right? And now let's look at the sum of radii objective, which is what we'll be focusing in this talk. So similar to K center, here the cost of a cluster is the radius of that cluster. But then like K median, the overall cost is the sum of all cluster costs. So it has similarities with both K center and K median. Sum of radii is not as well known as its siblings K center and K median. And even though it has similarities with both, it behaves kind of differently from them. And but even then, like some of the ideas from K center, K median literature are often useful for sum of radii. And now I want to talk about an equivalent formulation to look at the sum of radii problem. So now we want to find a set of centers, and then you place a ball of a certain radius around every center. And these radii can be different. So now you get a set of balls. And the objective, of course, is to minimize the sum of radii of these balls. So the difference here is that you're looking at these balls as the more fundamental objects. And this perspective is often more useful when you're designing algorithms. So let's look at a bit of history of the sum of radii clustering. So although it's not as well known, by no means it's a new clustering object. So the sum of radii problem was first studied by Charikar and Panigrahi in 2004, who gave a constant approximation in polynomial time. And they used a Lagrangian relaxation framework that was very similar to the Jain-Vazirani algorithm for K-median. So as I said, the ideas from K-center, K-median often carry over. Now there were subsequent results, like Gibson et al. Give a Q-pitas, which means that a 1 plus epsilon approximation in quasi-polynomial. And this kind of indicates that this problem is not APX hard, which is very different from K-center and K-median, which are in fact APX hard. And in some special cases like Euclidean metrics or some other special assumptions, you can get better results. A bunch of variations on this vanilla sum of radii clustering problem have also been studied. So suppose instead of minimizing the sum of radii, you want to minimize the sum of alpha powers of radii, where alpha is at least 1. So that has been looked at. Or the supplier version, where we have different sets of clients and servers. Or the fault tolerant clustering, where points need to be covered multiple times by different points. So there are constant approximations known for all these different variations. And now we are going to look at yet another variation, and this is the capacitated clustering. So of course, capacitated versions of different covering clustering problems have been studied. So they're meant to represent some kind of bandwidth constraints, like if some centers are providing some kind of service to the nearby points, then it can only provide service to so many points. So that's what this represents. And here we are looking at the uniform capacity. So we have this parameter U, which is the maximum number of points that can belong to a single cluster. And so the capacitated sum of radii problem is the following. So we want to find a set of at most k balls and then assign every point to one of these balls, subject to the following two constraints. So the first one is that if you're assigning a point to a ball, then the point has to be contained in the ball, which is fairly obvious. And the second constraint says that you cannot assign more than u points to any of the balls. So this is the capacity constraint. And the objective, of course, is to minimize the sum of radii. And as I said, polynomial time constant approximations are known for all the variations that I was talking about earlier. So the natural question is, can you do the same thing for the capacity constraints? But this kind of seems difficult. So like approaches like LP rounding, which are natural candidates for capacitated problems, they don't really seem to work. And there is another indication. So if you remember the variations that I talked about, then this is the supplier version of the problem, where you want to minimize the sum of squares of radii, let's say. And one can show that this problem is log n hard. And it's it's very similar to the original sum of radii problem that we are looking at. So this might be like another indication that even our sum of radii problem might be hard to approximate. So given these couple of indirect indications, like how do we get around this barrier? So of course, we looked at the capacitated k-center and k-median literature for inspiration. And now there are already constant approximations known for capacitated k-center. So that is pretty much set. On the other hand, getting constant approximation for capacitated k-median in polynomial time. So that is a long-standing open problem. And so faced with this difficulty for k-median, researchers have made like partial progress using one of two directions. So the first one is like bi-criteria approximations. So here you allow some small violations in the capacity constraint or the k constraint, and then you can get like a constant approximation. On the other hand, and this is like a relatively recent approach, where you don't allow for any violations in the original constraints of the capacitated k median, but then the running time of the algorithm is not necessarily a polynomial. So this was the approach of these two papers by Adamczyk et al. And Cohen-Haddad et al., who obtained a constant approximation for capacitated k median in a fixed parameter tractable time, which means that the running time is like a strict polynomial in n, but the dependence on k may be like exponential or worse. So remember that like n is the number of points and k is the number of clusters. So this sort of running time may be acceptable if the number of clusters is like a reasonably small constant, because then the overall running time becomes polynomial in n. And this is the approach that we take. So our main result is 28 approximation for the capacitated sum of radii clustering in using like an FPT algorithm. And the parameter here, of course, is k, which is the number of clusters. So we also consider a related problem, which is the uncapacitated sum of radii problem, along with a matroid constraint. So if you are not familiar with matroids, it's a combinatorial abstractions of many interesting structures. And I'm not going to define the problem here, but if you're familiar with matroids, then here you want the set of chosen centers to be an independent set in the given matroid. And let me just mention a couple of interesting special cases. So first is the uncapacitated sum of radii problem. So here you want to choose at most k centers. And remember, there's already a constant approximation known from Charikar and Pani. Now let's look at a variation of this setting where let's say the centers come in two colors, red and blue. And let's say you can choose at most R red centers and B blue centers. So this matroid formulation encapsulates all these different kinds of interesting scenarios. And we give a 9 plus epsilon approximation using a similar kind of FPT algorithm. And this algorithm uses similar ideas as our main result, but it's much more simple. So we like give it as a warm-up for our main result. And in this talk, I'll mainly talk about this capacitated sum of radii result. But I'll allude to the simplifications that can happen when you don't have capacity. So I'll start with our high-level approach for the FPT approximation. So let's fix an optimal solution to this problem. And if you think about it, it has three components. So first, it has to find the locations of these centers. And remember, the number of these centers has to be at most k. Then it has to assign a certain radius to each of these centers so that we get a bunch of balls. And then it has to find that assignment from points. And this assignment is subject to the two constraints that I mentioned earlier. Which is that if you're assigning a point to a ball, then the point has to be contained in the ball. And secondly, you can only assign at most u points to any of the ball. So we are going to try to imitate this optimal solution in terms of these three components. And now, of course, if we kind of wanted to do this exactly by enumerating all the solutions, then that will take at least n to the order k time, which is not really desirable. So we'll kind of approximately imitate the optimal by making some sacrifices here and there when we are enumerating. And this is what helps us bound the size of the search space. And that's how we get an FPT algorithm. So let's look at some of the details. So first of all, our algorithm would like to know how many balls of roughly similar size should be used in the solution. And this is what we call the radius profile. So now consider the balls in the optimal solution. And let's say we kind of round up every radius to the nearest power of 2. So this kind of increases the cost of the solution by at most a factor of 2. But more importantly, it has the effect of discretizing the radii. So let's say R1 is the largest radius, and let's say optimal uses K1 balls of this radius R1. Then let's say the next largest radius is R2, which is like half of R1. And let's say optimal uses K2 balls here, and so on. So let's say there are T classes of radii. And this is the like a useful knowledge that our algorithm would like to have. So like we don't know how to find this optimal radius profile in polynomial time. But using standard tricks, we can assume T, which is the number of classes, is order log k, which means that there are only k to the order log k radius profiles. And we can like try all of them. This is fine because we are only shooting for an FPT algorithm. So the optimal radius profile has to be one of these k to the order log k radius profiles. So from now on, we'll just assume that we are working with the correct one. So now that we know how many balls to use at every level, our algorithm is going to be recursive, and it works at levels 1 through t. So remember, t is the number of radius classes in the optimal. So it will start at level 1, it will do some work, then make a bunch of recursive calls to the algorithm at level 2, and so on. So when the algorithm is at level I, it has already chosen balls at levels 1 through I minus 1. And these balls have radii R1 through Ri minus 1. And remember, these radii are larger than Ri, which is what we'll be dealing with at this level. So there'll be many such recursive calls at level I, and we'll have the following inductive property. So amongst all the recursive calls, there'll be at least one call where the algorithm has successfully approximated the optimal behavior from like level 1 through I minus 1. And given this, our task is to do the same thing for radius Ri balls at this level I. Yeah. Okay, so let's see this recursive algorithm in more detail. So let's go to the start of level 1. So at this point, we haven't added any ball to the solution. So all the points are uncovered, right? And now if you look at the optimal solution, it uses K1 balls of radius R1, K2 balls of radius R2, and so on. So up to like KT balls of radius RT, right? And so overall, it uses K1 plus K2 plus up to KT balls, which is like at most K. And the radius of any of these balls is at most R1 because R1 is the largest radius. So this is like, so optimal can cover the entire set of points using at most K balls of radius at most R1. And this is like K center problem if you ignore the capacities for the moment. And there's like a 2 approximation for K center, which is what we use. So this 2 approximation gives us a set of centers of size at most K. And this set has the property that any point has at least one center within distance to R1. So let's look at a picture. So here we have a 2 approximate solution. So we have these K centers here, at most K centers. And the radius of any of these balls is at most 2R1, right? And all the points are covered by one of these K balls, at least one of the K balls, which means that even the optimal centers of level 1 balls are covered by these balls. So we have those centers here shown as blue squares. So optimal uses K1 centers at this level, which means that there is some subset of size K1, which is relevant in the sense that it approximates optimal at this level. So that will be like this, this center and this. So let's focus on that subset. So our K1 orange balls of radius at most 2R1, they are kind of the relevant balls here, but they don't really completely cover the optimal balls here. But that is very easy to fix. So instead of using 2R1 balls, let's say we use 3R1 balls, then that kind of completely covers everything that optimal covers at level 1. So to summarize, we know that there is some subset of size K1, which is relevant in the sense that it approximates the behavior of optimal at level 1. But our picture kind of looks like this. So we don't know which subset is relevant. So we know that there's some subset of size K1 which is relevant. We don't know which one. So we'll just try all of them. So there are like K to the order K1 such subsets. And we make a recursive call to the algorithm at level 2 on each of these guesses. And notice that if we started from scratch, then the number of subsets would have been like n to the order K1. So let's, so just by like like computing this intermediate 2 approximation to K center, we have cut down the number of recursive calls from n to the order K1 to K to the order K1. And this is going to be like a general idea even later on. So let's see what happens at level 2. And so let's focus on the correct guess, where our 3R1 balls completely cover R1 balls, right? And let's focus on these optimal balls, and let's look at this green region. So this green region are the points that are not covered by the optimal at level 1, which means that these points have to be covered using balls of radius R2 or smaller, right, by the optimal solution. And how many such balls are there? So there are K2 balls of radius R2, K3 balls of radius R3, and so on in the optimal solution. So overall, optimal uses at most K balls, and the radius of any of these balls is bounded by R2. And this may already sound familiar to you. So like, let's see what happens in our picture. So this blue region here, that is the set of points that we don't cover at level 1, which means that we have to cover these points at level 2 or later, right? But the crucial thing here is that this blue region is like a subset of this green region, right? Because our balls completely cover the optimal balls. So the complement, which is the blue region, is a subset of the complement of these optimal balls. And so we have to kind of cover the points in this blue region using at most K balls of radius at most R2. So it seems that like we can repeat the K center type of argument again and like keep doing this. And if you didn't have capacities, then that's exactly what you can do. And like that's what happens in the Matroid version. So you keep doing this until level T, and then afterwards there's some post-processing where we use like a certain Matroid intersection problem to get the final approximate solution. But here we have capacities, so and we have completely ignored these capacities so far. So like this argument doesn't work. So let's see what goes wrong. So let's say we have this optimal ball of radius R1, and we have this 3R1 ball, which is what we have chosen. So the optimal ball may contain a lot of points, but it may not have enough capacity. And so the optimal may not be able to assign all of these points to this R1 ball. And so it may have to use even smaller balls inside this R1 ball so that like now it has enough capacity, right? And this possibility we hadn't considered before, that optimal may be using like smaller balls inside like a larger ball. And so even though the K-center type of argument works outside these level 1 balls, it doesn't work inside for these smaller balls. And so to summarize, when we are guessing locations of level 2 balls, the guesses have to be made in this blue region outside level 1 balls, as well as in each of these level 1 balls. So the guesses have to be made in each of these orange balls and in the blue region. And in general, if we are at level I, then we have already chosen some balls which are larger from level 1 through I minus 1. And at any point in the algorithm, we have chosen at most K balls, which induces these kind of 2 to the K regions, right? And we have to do this kind of guessing in each of these 2 to the K regions. So let's look at this in more detail. So let's say this is the picture at level I, and these are the balls that we have added from like levels 1 through I minus 1. So they are larger balls and they're already fixed. So let's look at a particular region, let's say region 5 here. So this is induced by this small ball here and this larger ball. But these points are not contained in any other ball. For example, not in this ball or this larger ball here. So let's expand this region and see what happens. So let's say this is the expanded picture of region 5. And suppose the optimal is using 3 balls of radius Ri, right, inside this region. Now, of course, we don't know how many balls optimal uses here. So we just have to guess this number. But let's say we kind of correctly guess that to be 3. So we have to find the approximate locations for these 3 balls. So we use like a particular greedy algorithm. And we find these potential substitute locations, which are given in this black squares. And the greedy choice here is based on how dense the Ri neighborhood around each location is. So this like greedy choice is very crucial in the analysis. So this potential replacement locations, this set has size order k, and we'll use some of these locations to find like a unique replacement for each of these 3 optimal sets. So let's see. So some of these locations may be too close to an optimal ball and this radius is like smaller than Ri. So the algorithm hasn't seen these balls yet, or because these are at a later level. But if we choose a replacement center at this level, which is like too close to a future ball, then that will kind of mess up the inductive argument at a later level. So we'll just have to discard these bad locations. So again, we kind of don't know the locations of future optimal balls. In fact, we don't know the locations of any optimal balls. So we just kind of have to guess where the bad subset might be. But again, let's just assume that we kind of correctly guess the bad subset and we kind of get rid of those. So remember that we started from a set of size k. So like the number of all these guesses is purely a function of k. Right? So the property of this replacement set is that even after getting rid of these bad subset, we'll be still left with enough locations so that every optimal center will kind of find a unique replacement. So we started from like 3 optimal centers here. So we'll be left with like at least 3 replacement locations. Right? So we now just like map every optimal center to like a unique replacement location. And some of the optimal centers may be lucky because they find a replacement that is reasonably close. And this means that like a ball of radius, let's say 5 Ri, it will kind of completely cover the optimal ball of radius Ri. And this is good because all the points that are assigned to the optimal Ri ball, so all the points that are like inside this ball, they can already be assigned to the replacement 5 Ri ball because they are also contained in the larger ball. So this is like a good case. But then some other centers may not find a replacement that's like very close. And in this case, we have to like argue about the capacity reassignment. And the argument here is like fairly technical, but it crucially uses the following 2 things. So first of all, the careful greedy manner where we use the density of Ri neighborhoods to find these replacement locations. So that is like one fact which we use. And the second is that both the optimal center here and its replacement, they are contained in this like region or equivalence class. And so they're contained in like exactly the same set of larger balls. And in fact, we'll use those larger balls as like a conduit for capacity reassignment. So we kind of do this process for each of the 2 to the k regions. And so the overall number of guesses is some function f of k. And so we'll make f of k recursive calls to the algorithm at level I plus 1. And we know that at least one of these recursive calls is going to be correct in the sense that it properly approximates the behavior of optimal from level 1 through I. And so we kind of maintain the inductive condition. And so we kind of keep doing this until level t. And so now if you look at the recursion tree, then there are many leaves of this tree at level t. And because of this inductive argument, we know that there'll be at least one leaf at level t where we kind of find an approximate solution. So to summarize, we kind of get a 28 approximation for this capacitated sum of radii problem. And the dependence of running time is like 2 to the order k squared on k, but then it's like a strict polynomial in n. And as I mentioned, many of these details kind of simplify if you don't have capacities. So we get like a 9 plus epsilon approximation in FPT. And the parameter here is the like size of the base of the matrix. So so there are like a couple of open questions arising from this work. So first of all, we saw that there was some indirect indication that a polynomial time constant approximation may be difficult for this capacitated sum of radii, which is why we kind of resorted to an FPT algorithm. But like, can we in fact obtain a constant approximation in polynomial time, or can we show that that's not possible? So that's one open problem. On the other hand, for the matroid version, there is no such indication, even like an indirect indication, that a constant approximation is not possible in polynomial time. In fact, like matroid versions of k center and k median, they do have polynomial time constant approximation, which may be like a suggestion that or indication that the matroid sum of radii may also have a polynomial time constant approximation. So that's a second open problem. So I'll stop here. Thanks for watching my talk. And if you have any questions or comments, please come and talk to me during the poster session. Otherwise, you can also email me at my email address.